Hey, Calc 2 folks, back here with another demo in Mathematica, where this time around I wanted to uh, help you write up a couple of programs that are going to perform a few of the convergence tests for you, or the divergence tests for you, right? Some of these tests for convergence versus divergence, right? I do have 4 programs that I want to share with you in this demo that will go through the cases for the divergence test, the case for the integral test, the case for the limit comparison test, and the case for the alternating series test, folks. So to begin with, what you want to do, again, as always, is open up a new notebook. Make sure you give it a decent title. We'll say here maybe tests for convergence. Let's call it whatever you need to so that you remember this notebook. So I've gotten that successfully renamed. I'm going to hit Alt-4, bring up a title menu here. Now let's start with what is known as the divergence test, right? I might point out we're going to follow this with the alternating series test. We might follow that up with, careful there, gotta come back down. Maybe we do then following that with the integral test. And I'm going a little out of order here, folks. Reason being is that the alternating series test is very much like the divergence test, if we recall that. Then we had the limit comparison test, folks. In this demo, I do have some programs to share with you for these 4 respective tests. Now, if I go up to the excuse me, first test here, the case for the divergence test, and I consider a program for that, it is going to start again by, first of all, denoting the kth term of our infinite series as a function of k. Let's grab one. Let's go with the case where we have maybe the value 1 over k to begin with here. This is the harmonic series. We do know that it diverges, right? But in the divergence test, we're going to also encounter some inconclusive results, right? So let's see what happens here in the divergence test for this. Now remember, in the divergence test, what we are going to want to calculate is a limit. What we are calculating the limit of is f of k, as that value of k heads off to the value of infinity. Right? We are going to calculate this value of the limit for this result here, 1 over k. Now, what we might go ahead and do is call that value the limit L, right? And maybe I'll go ahead and set delay that to be the value of L. And what we're going to use here to make some judgments on the value of L is an if-then statement, right? The way that if-thens work is you're going to have an if statement, an if operator applied to, first of all, what would be the conditions in order to be true, followed by what would be the result if we do have a true statement, followed by what would be the result if we have a false statement. And if you need to, you can also have the case where if it's not true or false, you have the case for an inconclusive statement, right? What we're going to be working with is primarily the cases for true and perhaps the case for false in some of these conditions, right? Now, to begin with here, what we might notice is what we're judging is the value of L. So we might say here, if L equals 0, what does that tell us in a result to this test? And if you remember, right, when you calculate the divergence test and this limit as k heads to infinity is 0 in value, the test is inconclusive in its result, right? If you happen to calculate this value of L in the divergence test and it equals 0, right, that is the case for the test being conclusive. That is going to print that out when that is a true statement. When this condition is true, the program for Mathematica is going to print out the test as inconclusive, because that is the result that happens when this limit is 0 in the divergence test. Now, what happens if it's not 0? What if that case is false? Well, then what the divergence test tells us is that the series diverges, right? And that's it, folks. That is the program that performs the divergence test on a non-alternating series. For 1 over k, we saw this back in the notes, this result should be inconclusive. And if I run this program, it does tell me that. This test is inconclusive. If I go back and actually have it display the value of L, right? Here, certainly the value of L is 0 in value, right? I'm going to turn off that value of L, though, right? This is a case for the test being inconclusive. If I was to raise this to the second power, right? Again, that's going to be an inconclusive result in this test. But if I was to have, for instance, the geometric series given by 3/2 raised to the kth power, where here r, the absolute value of r, 3/2 is greater than 1, this is a divergent series. And if we run this test, it tells us that. This test does tell us that we have here a divergent series. All right, folks, that is the program we have here for the divergence test. Now, as I had noted, this test is very similar to the alternating series test. If I come down here and just simply copy and paste it over, I just have to make a few small changes. First of all, in an alternating series test, you are going to have an alternating series. So let's go ahead and make an alternating series here, and perhaps let's make the alternating harmonic series, because we know the alternating harmonic series is convergent, and the alternating series test should tell us this result, right? What we are going to want to do in this test is, if I declare f of k as the entire argument seen in my alternating series, then I'm going to want to evaluate the limit for what is the absolute value of f of k as k heads off to the infinity. Now, the absolute value, what that does is it does eliminate the alternating aspect, the -1 raised to the kth power. It really only considers the behavior of 1 over k. Now, if I was to leave off this description of the alternating behavior, having that absolute value there is going to have 0 effect on the results of this test. Like we said, the absolute value of that alternating series is 1 over k. This is what it's going to be calculating the limit of in the end. So if you happen to leave in or state this series here with that actual alternating aspect left in the calculation, right, or in that description of f of k or a sub k, having absolute value of f of k inside your limit operation here will handle that alternating aspect. Now, what you want to remember in the alternating series test, it is different than the divergence test in how it's interpreted in this if statement down here. In the alternating series test, where we see a difference is if this condition is true, if the value you calculate for this limit does equal 0, what that tells us, right, is that the series converges. Versus what we saw in the divergence test for a non-alternating series, if that limit was to equal 0, that would actually give us an inconclusive result. Other than that, folks, right? Other than that, as long as we're applying this in the case of alternating series, this is the program. If I run it here, it will tell me, yes, the alternating harmonic series is convergent. Whereas if I set up, for instance, the case for a p-series here, the alternating p-series where p equals 1/2, in this case I do think, well, let's see what we get. Well, the series converges again. The value of the limit must be equal to 0. And actually, we can see that if we spend some time with that limit. If we went with definitely a divergence situation, we might consider the geometric series 3/2 raised to the kth power. Whether that alternates or not, we should see some divergence, and certainly we get that result here. This tells us that test result diverges. All right, folks, so that's the second of our tests. That's the alternating series test. Let's go on to the third case here. In the third case, again, we're working with a non-alternating series. So let's put up here a non-alternating series. Maybe we go ahead and grab the harmonic series here. Remember, the harmonic series was proven to be divergent using this test back in our notes. The integral test, the first example we did was for the case of this harmonic series, and we showed that it was divergent. Now, this integral test is going to require us to take note on what is a proper lower index in the series. The lower index here in this particular series, we might make it the value of 1. Certainly, we don't want to have a lower index of 0 because our first term would be undefined in this result, right? In this series, this is a case where C would be conveniently the value of 1. Now, keep in mind what we want to do in this test is we are going to integrate, right, the value of f of k, right, over values of k starting at C and heading up to infinity. Now, this is the case for an improper integral, and I will tell you, I've run into times where Mathematica does not like improper integrals. If I attempt this one, you can see here it does give me kind of a bizarre result, right? And that is because we don't have a convergent behavior here. What I would be better off to do is to approach it as we should technically approach an improper integral, and that is putting an upper bound on this integration at b, and then pushing b towards infinity in the form of a limit. So we'll go ahead and wrap this limit, or this integration calculation, where I've replaced the upper bound of infinity with the value of b, and then have that b head off to infinity in the calculation of this limit. You will now see when I calculate that limit, I get a nicer result. It tells me it's infinity, right? Which is what we calculated, which is describing a convergent behavior. And remember here, the interpretation of that, we might call this the integral. And I got to be careful using the word integral. That's kind of a reserved term. So let's just go with int, and I'll go ahead and make them capitalized. Right? This is the integral we're calculating in this test. We know in this case it's going to give us infinity. We need to have an interpretation of that, and that's where our if statement comes in. Right? If, let's see here, how did I do this? Let me just double check my note here. What we judge is if that integer value, or that integral value is less than infinity. Right? If that happens to be less than infinity, then we are going to print, right, this result. And remember, if it's less than infinity, we know the series converges. Let's just keep that all lowercase as a nice sentence there. Right? The series ends up converging. Whereas the false result here, right, if that integrand that we calculate for this improper integral in the integral test, if that is equal to infinity or heads towards infinity, like we see it happening here in the harmonic series, then that is the case for a divergent series, right? If the improper integral diverges, so does the series. If the improper integral converges, so does the series. So if we see it head to infinity as an integral, that is the case for divergence, and we would see the case for the series diverges. Right? So if I go back and now run the test, it does tell me the series diverges in this case. Whereas if I was to perform it on a convergent p series where p equals 2, We can see there it tells us the series converges. If I was to look at maybe another case where we know things converge, maybe we consider a convergent geometric series, right? 1/2 raised to the kth power is a convergent geometric series. Well, it tells me it converges, right? Whereas if I was to make that a geometric series where r equals 3/2, we should understand that that is a case for divergence. And certainly the test tells us that result, right? So again, this is the integral test, folks. This is the program that will actually perform the integral test for you, all right? We barely adjusted this C. We really weren't concerned with it, but at times you do want to take note of what is your lower bound in the series. Some series you don't necessarily want to start at a lower bound of 0. That could because that C value actually does set up the lower bound in this integral calculation. And if that C value happened to fall on an asymptote, you would have an improper integral caused by that, and we've seen some bizarre results from that. So make sure that you get a nice definitive value for this lower bound that is given to you from the series. All right, that value is C. Now the last case we have to look at here is the case for the limit comparison test. All right, folks, in the limit comparison test, we're going to actually have a few more inputs into this test compared to the tests given above. To begin with, you're going to need your given series. Now, I have been using function f to denote that, thinking that a sub k, the arguments of our series being expressed as explicit functions of k. If you want, you can always call f a if you want to, right, in your notation. In fact, we might consider doing that here just to mix it up a little bit. So maybe a sub k is our given series, and it's given by a, this function of k, where let's compare, maybe we go with 1 over k, let's grab a quantity here, k squared plus 1, right? And let's compare that to a known series. Now, the way we've denoted known series in this test is we called them b sub k, right? So instead of calling it some other function like f or g, let's just go ahead and use a and b here. So b sub k, what we might compare this to, now again folks, to use this test, you have to already have a series ahead of time that you know that you want to compare to. And here it might be convenient to compare to 1 over k squared, right? Where what we're going to have to note is b's behavior, right? We're going to have to take note on, to begin with here, what is the behavior of b? Not only do we have to know a b to compare to, but we have to know its behavior. And there's one of two types of behaviors we could have. We could have convergent behavior, or we could have divergent behavior, right? So maybe we set up some ground rules here and say that C is going to stand for convergent and D is going to stand for divergent. And in this case, we know C is convergent. So let's make that a big C there, right? Let's say B's behavior is convergent, and we denote that with just the value of C, right? And we can keep track of it with this little bit of documentation. And in fact, this is how you document in Mathematica, folks. It is essentially a statement surrounded by stars and parentheses. That will create documentation. If I wanted to document these series, right, I typically make my statement like that to begin with and then jump back into my documentation and say this is the known series in my test, whereas this is going to be the given series in my test, right? That is how we document in Mathematica. We can document, I think usually it's line by line is what we document over. So that is documentation, folks. Now, as for the test itself, that depends upon the value of a limit, all right? The limit of what is the given series divided by your known series as k heads to infinity. Right? And again, remember how I'm making this right arrow in these limits is I am using a minus sign followed by a greater than symbol without the space. When you bring those together, you do see that you get that right arrow formation, right? So this would be the limit that we're going to calculate, where we're going to have to make a judgment on this limit. So let's go ahead and call this value L in our calculation, right? And this judgment is going to be made with some if statements. All right. The first if statement we're going to make here is the if statement, right? That's going to look at B's behavior. If B's behavior is equal to the value of C. Now in Mathematica, folks, to denote things equal to each other inside conditions, you do have to use a double equal sign here. This denotes equal to. If I wanted to do less than or equal to, I would do a less than sign and then an equal sign. And that will give me a less than or equal to. If I want to do a greater than or equal to, I would do a greater than sign and an equal sign. That would give me a greater than or equal to. You need two symbols together to set up some of these conditions. So like equals would be two equal signs, right? If we wanted to make a combination of rules, if we wanted to add an intersection in here then in this condition, I would use a double and sign. And if I wanted to make the statement of or, how do I do an or? You look up an or. Or is what you would expect. It's this double absolute value symbol, right? That would be an or statement. If we wanted to talk about this and or another condition, we could use that double absolute value. Here we only have one condition. We're only interested in B's behavior in this if statement. Now keep in mind we're going to have a true result, and we're going to have what we would think of as a false result. But I will tell you here, folks, we're not really going to make use of the false result. And you can do this in if statements, especially when your if statement involves a nested if. What we're going to have here is a nested if statement. This if statement is only going to activate when this condition is true. Once it activates with this condition being true, it's going to put itself into this if statement, the true condition for this situation, right? And what we're going to look at inside the nested if here is this value of L. We're going to be interested in it being greater than or equal to the value 0 or smaller than the value of infinity, right? When that is true, right, what we know is the series converges, right? Whereas if that is false, that false statement would fall right here, right? If that is false, we would print the statement, the series diverges. Whoa, no, careful there, not diverges. The test is inconclusive. That does give us the case for an inconclusive result, right? This test would actually be inconclusive with that result, all right? And what you will notice, this is the false statement for the first case of if, and we're really just going to leave that blank, right? I imagine we could have tied in what's going to be a second if statement into that location, but I prefer to leave the two separate here as it's a bit of a better illustration in my argument would be that it's a better illustration of what the limit comparison test is actually doing here, right? The limit comparison test result, how it's interpreted, all depends upon the behavior of B, the known series, right? That's what sparks which case we're going to be jumping into in terms of these two if statements. The second if statement is the case for the false statement for the other situation, but I like to be a little more explicit with it and force it in there with that value of D, right? If B's behavior is divergent, we will perform this true thing, or we will have this false statement that we're not going to use. In fact, what's going to happen here, as soon as we set this to D, it's going to automatically force itself into this if statement. And once forced into this if statement, because that D is true, it's going to then force it into this if result, right? So this is a way of just embedding some if statements. It kind of gets away from having to set up a bunch of intersecting conditions here, right? That's also what I'm trying to avoid is setting up a bunch of intersecting conditions where it's a little bit more obvious as to how how you could perform this test algorithmically, right? And it does begin by just noting what is your behavior of the known series. Does it converge or diverge? If it's converged, you want to think about things this way. And if it diverges, you want to think about things this way. And that being, you move to your value of L. If L is bigger than 0, now notice in this case it's not equal to, but less than or equal to infinity. In this case, we can equal infinity. When that is true, the result of the test is divergence, right? This series diverges, we might say, right? We might use that statement there. The series diverges. When L is bigger than 0 but doesn't equal it, and is less than or equal to the value of infinity, that's going to cause a divergent result in this series. Whereas if that doesn't happen, as with the first case, right, we go back and say the test is inconclusive in value, right? The test doesn't really tell us much. And we have to go back and try some other alternative test. Right? Folks, this is the limit comparison test. Now let's see what we get as output here. Right? 1 over k squared and 1 over k squared plus 1. 1 over k squared plus 1 is divergent. Or sorry, convergent. Because when compared to this, it is very similar to this, and this is also convergent behavior. And if we run the test, we do see the series converges. Now we do get some of these other results. The only reason it's spitting out this result is because it's trying to compare C to D, and it's having some issue with that in its interpretation. And that's why I will turn these if statements off, right, with some semicolons, as well as I don't necessarily need that semicolon for inside this L statement here. So this will really clean it up and just tell us the result. The series converges. All right? And all I did was add semicolons to the end of the if statements and the end of L here. If you want to actually see the limit, you would leave the semicolon off, and that would tell you the value of the limit there. All right? In that particular case. Now let's see if we can compare a divergent series. Let's say we were to compare, let's go with this case. Let's say we had 1 over k raised to the, well, let me clean that k up. That's our known. Let's go with k plus 1 raised to the 1/2 power. What we're going to compare that to is k to the 1/2, which you will note is a p-series where p is equal to 1/2. And in that case of a p-series, we know the result's going to be divergent. Right? So does the test tell us that we get a divergent result here? Run the test. The series diverges. All right. Now, let's consider maybe running this test. What if I had, let's see if we can get an inconclusive result out of this. I think I did run a test, a test that might give us an inconclusive result. What if we say we had k cubed, right? K cubed we know is divergent, right? And let's say we were to compare it to k squared, which is also a divergent series, right? Both of them obviously divergent. This, right, is a divergent series. This is a divergent series. This is where a p is a p series, right? Where p is what, less than 1 in value, right? It's negative 1/2. Here's a p series where p is negative 3. Both divergent cases. And if we set that b's behavior as divergent and we try to perform this test, it does tell us, is that right? Yeah, it does tell us that series diverges, right? That is a divergent result. When I'm looking for, what if I try to compare that to 1 over k squared, where I know that is convergent? There, that tells me the test is inconclusive, right? In a sense, maybe the test is not appropriate to apply at this point, right? Or that the result itself, again, can just not be interpreted, right? Folks, this is 4 tests for convergence, right, that we were introduced to in sections 10.4, 10.5, and 10.6 material, right? In those those 3 sections, we were introduced to these 4 tests. The only test I don't have here is the comparison test, folks. The comparison test, really, I was thinking of programs that I could write for that. And every program that I thought of, because it's not so easy to have Mathematica actually do what is needed in the test, and that is observing this behavior of being bigger than or less than when convergent or divergent. Perhaps there's some way to look at it, but the way that I started to look at it is essentially just the limit test, right? It really does involve, how do you know if this is bigger than this? How do you know when the given series is bigger than the known series, or the known series is bigger than the given series? Is you do look at the limit of the ratio, which is what the limit comparison test is already doing, right? And the limit comparison test works right alongside with the comparison test. If I think of these 2 series here, 1 over k plus 2 squared and 1 over k squared, right? These could be shown, right? The given series could be shown to be convergent using the limit comparison test, right? Or even using the comparison test is where I meant to go with that. And notice you do get a convergent result also from the limit comparison test. So comparison test, it's kind of a shortcutting the limit comparison test. It is a way of kind of shortcutting the limit comparison test, because all you're really doing is analyzing and comparing the growth rate of a sub k to the growth rate of b sub k, which is what this limit does in its calculation, right? But if you cannot see how you might show that a sub k here, in this case, is always smaller than 1 over k squared, b sub k, then the limit comparison test is going to be the direction you want to head, right? So, folks, this is the, again, a quick little demo where I rolled through those 4 tests for you, folks. Those 4 fundamental tests for convergence or divergence, for testing infinite series for this behavior. I hope these 4 programs help you to understand the tests a little better, and what they allow you to conclude in some cases, and when they give back inconclusive results in the other, right? And I hope that along with that, it helped you learn a little bit more about how to use Mathematica. It is, like I said, an extremely useful programming language to become familiar with, and I hope that you are. I hope that you're hanging in there, and I hope everything's all right. As always, you know how to get a hold of me, folks. And I hope you have a good day and a good weekend. And I'll see you next time.